Today's lesson is on polynomial functions and graphs. So what we're going to do first is we're going to sketch the graphs of the following polynomial equations. We're going to identify their end behavior. This is a new word for you. Whether the leading coefficient is positive or negative, and the degree of the function. And I'm going to show you how to find all of those based on the equations. So the first thing we're going to start off with is x squared. So when we graph y equals x squared, this is just a parabola going through 0, 0, opening up. And again, this is just a sketch. When we talk about the end behavior, we are looking at what's happening at the end. What is happening at the end? All right. So we look at, all right, well, what's happening at the left, right? As we're going to the left, where is my graph going? Well, it's going up, and it's going to keep on going up forever. So we're going to say when we go to the left, the graph is going up towards positive infinity. Then we look, okay, well, what's happening as I go to the right? Well, my graph is also going up. So we're also going up towards positive infinity. Then we look at the leading coefficient. My leading coefficient is a 1. It is positive. The degree of the polynomial comes from the degree of the greatest degree of the polynomial. So in this case, it's a 2. That number 2 is even, right? So the degree is 2, and this is an even number. Okay. Next, we have y equals x to the third power. So when we graph y equals x to the third, we get a graph that looks like this. So now we say, okay, well, what's happening as I go to the left? Where is my graph going? Well, it's coming down. It's going down towards negative infinity. What's happening to the right? It's going up. So as we go to the right, my graph is going up towards positive infinity. So we can see here the leading coefficient is a 1. It is positive. The degree is 3. So that is an odd number. If we graph y to the fourth power, and again, you can use a table, you can use a graphing calculator. This is going to look very similar to x squared, except it's going to be almost a little bit flatter here and just a little bit wider, so like this. And now, again, when they ask for end behavior, what's happening at the ends of the graph? We don't care about anything that's happening inside. We're looking at just those end points, those end behaviors. So if I go to the left, it looks very similar to our x squared. As we go to the left, my graph is going up towards positive infinity. As we go to the right, it's also going up towards positive infinity. My leading coefficient is 1, and it's a positive 1, so it's positive. And the degree of the polynomial is 4, which is even. Next, if I graph 2x cubed plus 3x plus 1, it's going to look something like this. So if we look at the end behaviors, I'm going to circle them. As we approach the left, as we go to the left, my graph is going down towards negative infinity. As I go to the right, my graph is going up towards positive infinity. My leading coefficient is 2. It is a positive 2. And my degree is 3. That is the greatest degree in the polynomial. So this is 3, which is odd. So we should see a little pattern of those end behaviors with the degrees and the positive, right? The degrees of their even or odd. Notice that the evens are going towards positive infinity. And both odds go in opposite directions. One's going down from going towards the left, and when we go to the right, it's going up. So when they're odd, the end behaviors are going in opposite directions. Okay. Next, we look at negative x to the 4th power. So when I graph a negative x to the 4th power, it's very similar to x to the 4th, except it's going to reflect across the x-axis. So it looks like that. So now when we look at the end behavior, it's a different color. Red, down, and down. So as we go to the left, my graph is going down to negative infinity. As I go to the right, we're going down to negative infinity. My leading coefficient here is a negative. The degree of the polynomial is a 4, which is even. All right, next one we're going to graph is a negative x to the 3rd. So if we look at our positive x to the 3rd, we're going to reflect that across the x-axis. Whatever's going towards the bottom is now going to go up, and whatever was going up is now going to go down. So that's going to look like that. So now my end behaviors again are going in opposite directions. As we go to the left, my graph is going up towards positive infinity. And as we go to the right, my graph is going down to negative infinity. The leading coefficient is a negative number. And the degree of the polynomial is 3, which is odd. Again, look at the evens. All of my evens, the first one, the third one, and this first one here, all have end behaviors that go in the same direction, both going down, both going up here. When they're odd, they're going in opposite directions. Let's see if that holds true. We have x to the 5th power. So that graph will look something like this. Negative x to the 5th power. And again, we're going in opposite directions for my end behaviors. So as we go to the left, my graph is going up to positive infinity. As we go to the right, we're going down towards negative infinity. Again, the leading coefficient is negative. The degree of the polynomial is 5, which is odd. Again, we're going in opposite directions. And then our last little sketch here is a negative 3x to the 4th minus 2x plus 5. That is going to look something like this. Maybe a little more like that. Again, it's just a sketch. It's not going to be perfect. All I care about really here is identifying those end behaviors. So they're both going in the same direction. When we go to the left, the graph is going down towards negative infinity. And as we go to the right, the end behavior is going down towards negative infinity as well. That leading coefficient is a negative. The degree of the polynomial is 4, which is even. So here we should be able to see that as if we have a even degree, right, they're going to be going in the same directions, either both going up or both going down. If they're odd, we're going to be going in opposite directions. If the coefficients are positive, I want you to notice that both of these are going up, right? When we have an even, both are going up. Now for the odd ones, I want you to think about this being linear. If we have a positive odd, that's the same thing as a linear function, right? If it's linear, y equals x, that has a degree of 1. That makes it odd. And it's positive. Think of this as being a linear graph with a positive slope. The end behaviors are going to be the same. All right? So when we look at creating a little chart to help us with all this, it helps to think about linear and quadratic functions to get the end behavior for all positive, negative, even, and odd functions. So the end behavior of a polynomial function relies on the values of both the n and the a of the leading term. So we always make sure that it is in standard form, and we want to look at that first term in the polynomial. The a value right here is our coefficient. This is where we ask ourselves, okay, is my a positive or is it negative? Then we look at the n value. Is that an even number or an odd number? And then we're going to look at where that lands in our little chart, and then we'll understand what those end behaviors are. So if we look at here, we have a is positive, n is even. So positive and even, I think of a quadratic, right? I think of x squared. And I'm just thinking about the end behaviors of x squared. I don't care about what happens inside. I know that the graph has to look something like this, so my end behaviors need to both be up. So all I'm going to do here is just the end behaviors. I do not care about what happens inside, because I could have a crazy polynomial that's going to have all these things inside. But the inside doesn't matter. All that we care about are the end behaviors, what's happening at the end. So that's all I'm going to graph here. This is what our function end behaviors are going to look like. They're going to be both going up, going from the left and to the right. So if we use x squared to help us with that, it makes it really easy to do. So we ask ourselves, we read this as x approaches. So that arrow symbol means approaches. So as x approaches negative infinity, that means as we go to the left, my function, my y value, right, that's the y's, is going up. We're going up to positive infinity. And as the x approaches infinity, so as we go to the right towards positive infinity, as my x's go to the right, my f of x or my y's are also going up towards positive infinity. Now what happens if that function is negative? Well, remember, when our a value is negative, that's just going to reflect it across the x-axis. So now, instead of going up in both directions, we go down. Both end behaviors will be going down. So here, as x approaches negative infinity, so that means that as we're going to the left, this way, my graph is going down, my y's are going down to negative infinity. And as x approaches infinity, so as we go to the right, the y values are going down to negative infinity. This will happen for any polynomial that has that a that's positive and even, and a is negative and even. Now, what happens if it's odd? If we use our y equals x to the third, and again, I like to use y equals x, so let's go ahead and use y equals x. Again, this is something that we're used to. Y equals x, we know that. That's a line. That means that if I have a line with a positive slope, we want to be going up from left to right. What's happening in between, I don't know. But we know that anything with an odd exponent and a positive a is going to give us this type of end behavior. So as my x's approach negative infinity, so as we go to the left, my y values, my f of x, are going down. So as we go to the left, we're going down to negative infinity. And as we go to the right, as we approach positive infinity, the y values are going up towards positive infinity. So again, anytime your n is odd, we want to think of opposite directions. When they're even, when our power is even, this is, oops, not even. Let me put on here. These are the same. We're going to be going in the same direction. So if I'm looking at an example when my a is negative and I think of y equals negative x, we think of a negative slope. We're going to be going down from left to right, so here to here. So here's my end behaviors. Again, when we're dealing with a polynomial that has an odd exponent and an even and a negative a value, our graphs are going to look something like this. We don't know what's going to happen in between. The only thing we're guaranteed are the end behaviors. The fact that as x approaches negative infinity, meaning we're going to the left, my y values are going up towards positive infinity. As we go to the right, as my x approaches positive infinity, my graph is going down towards negative infinity. So this right here will help you get the hang of eventually not needing it, but identifying that a values, the degrees, and then we can use what we know to help us get those end behaviors. So number one here says, draw arrows to describe the end behavior for each polynomial and fill in the blank. So we have to look at our leading term. This is a leading term. It's in standard form. We can see that the 3 is positive, so I'm going to put right here positive. The 2 is even. So when I think of positive and I think of even means it's going to be both going in the same direction. Positive means they're going to be going up. So my end behaviors are going to look like this. I'll move it over. Both up. So as x approaches negative infinity, so as we go to the left, my graph is going up to positive infinity. And as we go to the right, as x approaches positive infinity, my graph is also going up. Next, we have a negative x to the third. So my coefficient is negative, and that exponent of 3 makes it odd. So I know that since I'm negative, and I'm odd, I have to think of a negative slope. So what does a negative slope of a line look like? It looks like this, which means my end behaviors are just going to look like that. So as my x approaches negative infinity, so as we go to the left, my graph is going up towards positive infinity. And as we go to the right towards infinity, so as we're going to the right, my graph is going down to negative infinity. Number 3, we're looking at negative 5x to the 4th. So we have a negative, because it's a negative 5, and the degree is a 4, which is even. So we know since it's even, they both have to be going in the same direction. And since it's negative, they're both going to be going down in this from left to right. So as my x approaches negative infinity, so as we go to the left, my graph is going down to negative infinity. And as we go to the right, my graph is going down towards negative infinity. Next, we look at 7x to the 5th power. So my 7 is positive, my 5 is odd. So we know for sure we're going to be going in opposite directions. So again, I think about if it's odd, we go in opposite directions. As it's positive, I think about a positive slope. Well, a positive slope goes up from left to right. So as my x's approach negative infinity, so as I go to the left, my graph is going down to negative infinity. And as I go to the right, my graph is going up towards positive infinity. Number 5, we have a negative x squared. So we have a negative coefficient. And since we're squared, we have an even degree. So because it's even, we know we're going to be going in the same direction. And because it's negative, they're both going to be going down. So as x approaches negative infinity, so as we go to the left, my graph goes down to negative infinity. And as my graph goes right, we also go down to negative infinity. And the last one, we have a negative 12x to the 7th power. So we have a negative coefficient and an odd exponent, or an odd polynomial degree. So negative and odd, again, they're going to go in opposite directions. I think of a negative slope, and my negative slope goes down from left to right. So it's going to look like that. All right, again, I just think of a negative line. Has a negative slope. So its end behaviors are, as we approach our graph, as we go to the left, as x approaches negative infinity, my graph is going up towards positive infinity. And as my x is going to the right, as my x is approaching positive infinity, my graph is going down towards negative infinity. And then the last thing we're going to look at, we're going to use the graph below to fill in the missing information from the table. We're going to label the graph by using the appropriate code and term. These terms are going to be very important. We have local maximum, local minimum, absolute maximum, and absolute minimum, also known as global min and global max. X-intercepts, y-intercepts. We want to know what interval is the graph increasing. So when do we have like a positive slope almost? And then when are the intervals of decrease? When are we going down? And then where are there any turning points? Okay, the points at which the graph changes from increasing to decreasing. All right, so what we're looking at here is we're going to color code those, and we're even going to circle and square in specific things if they exist. So looking at the local maximum, the highest point on a graph in a given area. So looking at our graph here in green, I'm going to color in the maximum. So we have, do this in a different green, one here and one here. So there are actually two local maximum. So we have this one here is at 3.5, 2. So we'll call that negative 3.5, sorry, negative 3.5. comma 2. And then the other one is at 1, 2, 3, 3. The local minimum is the lowest point on a graph in a given area. And we're going to do that one in blue. Use a different blue. Here we go. See it better. That one is going to be right there. So this one looks like -1/2 and -3/2, we'll estimate. So -1/2 or -0.5 and -3.5. Now, the absolute maximum, this is the highest point on the entire domain of the function. So local maximum is just, okay, where are all of our maximums? The absolute is, okay, well, from all of these maximums, which one is the highest? We're going to circle that point. So that's going to be this one right here. That is the absolute maximum, which is 3, 3. Now, an absolute minimum is the lowest point on the entire domain of the function. Well, we don't have an absolute minimum. We have a minimum, we have a local minimum, but we don't have an absolute. And the reason is there's only one point possible. So if you only have one point possible, that is a local minimum or a local maximum, because there's nothing to compare it to. We have n behaviors here. There is nothing to compare that point to. So we just call that a local minimum. So here, there are none. There is no absolute minimum. And again, there's only one minimum value. So there's nothing to compare it to. X-intercept, the points at which the graph crosses the x-axis. This one's going to be really important later on as well. We're going to color those in black. So we have 1, 2, 3, and 4 x-intercepts, right? These are at -5, 0, -2, 0, 1, 0, and 5, 0. My y-intercept, the point at which the graph crosses the y-axis, we're going to do in purple. So that's right here at 0, -3. Now we're going to be using interval notation here. Interval notation with the x values, it says an interval in which the y values are increasing. So looking at the graph, we just want to look at the graph and say, oh, where am I going up? Where is my graph increasing? Where would my slope be positive? I'm going to do that in yellow. Change that. So where is it increasing? Here up until we get to the green point. And here from that blue point, the minimum, up to the maximum. All right here, we are increasing. Now, we want to be careful when we say where they're increasing, we don't include the points where it stops, because it's not going to be increasing at the point. So we know we're going from -infinity to 3.5, a -3.5, and then from -0.5 to, 3. So the way we write that, remember, we're looking at intervals in which the y values are increasing. So we're looking at x values. Okay, we're looking at x values. So when we look at the highlighted part, we're going from a -infinity, because we're going to the left, up to whatever x value this is here, which is a -3.5. So we're going to write down, we're going from -infinity to -3.5. And so we're going to use that u for union, and we're going from this point, which is -1/2, up to this point. So this is negative 0.5 to 3. So those are the intervals which we're increasing, where the graph is going up. The y values are getting larger. My decreasing, we're going to put in red. So an interval in which the x value, it should be here, the y values are decreasing. So where are my y values decreasing, not x? I'm going to change this here. So in red, I'm going to put that interval. So here we're going from here, which is negative 3.5, down to the blue, which is negative 0.5. And then from 3 this way. Now remember that we're looking at the x values. So here, this was negative infinity to 3.5, and this is positive infinity over here. So the interval at which we're decreasing is from negative 3.5 to negative 0.5. And from 3 to infinity. This is very important for pre-cal or any higher level math, is being able to identify where graphs are increasing and decreasing. All right, now the turning points. These are also called points of inflection. Okay, these are also called points of inflection. Actually, no, not this one. So here it says the points at which the graph changes from increasing to decreasing, right? Points of inflection is something else. Don't worry, sorry I said that. So we're looking at where it goes from increasing to decreasing, right? So we can see here, there's going to be 3 turning points. So it changes from increasing to decreasing here, then from decreasing to increasing here, and then from increasing to decreasing up here. So there are 3 turning points. So based on the graph, polynomials are continuous functions. The leading coefficient is positive or negative. Well, looking at this, where our end behaviors are both going down, so we know that has to be negative because we're going down. And because they're both going down, this has to be even. So again, based on the graph, we know that we're going to have a continuous function. Notice how there's no holes, there's no gaps. We have end behaviors that are both, right, if we look at the end behaviors, are going down in both directions. So we know for sure, since they're going down, they're going to be negative. And because they're both going down, that means that it's even. In class, you're going to be working in your groups to do some more practice problems on these. So make sure that you have written everything down and you're ready to work in class.